Let me ask you something. If you press the brake pedal in your car, how long should it take before the brakes respond? A second? Half a second? Obviously, immediately, right? That expectation, that a system responds within a specific time, is exactly what engineers mean when they talk about real-time systems. And today, I want to show you what that actually means in the world of embedded systems. When people first hear real-time, they usually think it just means really fast. But that's actually not the point. Real-time systems are about being predictable. Engineers need to know exactly when something will happen. Think about systems like anti-lock braking, pacemakers, industrial robots, or even drones. These systems can't just respond whenever the CPU feels like it. They have to respond within a guaranteed time window. So here's the key idea. A real-time system is a system where timing matters just as much as the result. In other words, getting the right answer too late is still the wrong answer. Engineers usually divide these systems into two types. First, hard real-time systems. These are systems where missing a deadline is basically a failure. Think airbags in a car. If the airbag deploys even a little too late, it's useless. Then you have soft, real-time systems. These still care about timing, but missing a deadline occasionally isn't catastrophic. Things like video streaming, audio processing, or user interfaces fall into this category. Now, inside a microcontroller, something like an ESP32 or STM32, real-time behavior is usually managed by something called an RTOS, or real-time operating system. Think of it like a traffic controller for tasks. You might have one task reading sensors, another controlling a motor, and another sending data over Wi-Fi. The RTOS makes sure each task gets CPU time exactly when it needs it. One thing engineers pay close attention to here is something called interrupt latency. Basically, how long does it take for the processor to react when something important happens? If a sensor triggers an interrupt, the microcontroller has to stop what it's doing and handle it quickly. This is why when you read a microcontroller datasheet, you'll often see specifications related to timers, interrupts, and scheduling, because those are the things that determine whether the chip can actually handle real-time workloads. Now here's the part that gets interesting in real projects. Even if your code is perfect, real-time systems can still fail because of things like timing jitter, poorly prioritized tasks, or blocking code. For example, if one task holds the CPU for too long, other tasks might miss their deadlines. That's why debugging real-time systems often involves measuring timing with oscilloscopes or logic analyzers. Let's imagine a simple drone controller. Every few milliseconds, the system needs to read sensors, calculate orientation, adjust motor speeds, and maybe send telemetry data. All of that has to happen in a tight control loop. If that loop runs late, even by a few milliseconds, the drone becomes unstable. That's a perfect example of a real-time system in action. A lot of beginners assume that if their microcontroller is fast enough, then everything will just work. But speed alone doesn't guarantee real-time behavior. The real trick is task scheduling, prioritization, and timing analysis. Without that, even a powerful processor can miss deadlines. So let's quickly recap. A real-time system isn't defined by speed, it's defined by predictable timing. Hard real-time systems cannot miss deadlines. Soft real-time systems tolerate occasional delays, and microcontrollers achieve this behavior using interrupts, timers, and task scheduling. If you're getting into embedded systems, understanding timing like this becomes incredibly important. It's one of those concepts that shows up everywhere once you start building real projects. If you enjoy learning embedded systems this way, clear, practical, and engineering-focused, consider subscribing and sticking around. There's a lot more to explore.